Let's talk a little bit about the water cycle, which we're all familiar with. In fact, we're all part of the water cycle. Every moment of our lives, we might not fully appreciate it. So let's just jump in the cycle. I'll start with evaporation. So we could start with the surface of the ocean here, or this river, or this lake. And at any given moment, there's going to be water evaporating off of that surface. Water molecules that were in their liquid state, they just have enough energy to bounce away and go into the gas state. And water in a gaseous state we call vapor, water vapor. Water vapor. And so that water vapor, it is going to rise likely with the air that has been heated on the surface due to the sun. And there's other more complex dynamics at play. But as it rises and as the overall temperature cools, that water vapor will condense into little droplets. And it'll condense around little tiny air particles, little particles of dust that you can't even see with your eye. And that's what forms clouds. So this is little droplets. So the water is actually back to the liquid form. They're not individual water molecules anymore. They're now able to interact with each other, and they're condensing around these little microscopic dust particles to form these water droplets. And if it's cold enough, they might also form small ice crystals. And that's what clouds are. And we see here they're talking about transportation. You can have these clouds. We obviously, if you look outside and you see clouds, those clouds are moving with the wind. And so they could be moving all of those droplets with the overall wind. And when those droplets get heavy enough, they will precipitate down. Now, they could precipitate back into where we started. They could go back to the ocean there. Or you could go onto a mountain here, and since if the air is cold enough and if you have the right conditions, that precipitation might be snow, and it might stay snow right over there, or ice. But then eventually things might warm up, or they might not warm up. But if they do warm up, well, then they would melt, and then they would be snow melt runoff, and that's what you're seeing there. If that rain is falling in this area, and let's say it's not cold enough for it to be snow, so that we are talking about rain. Well, most of that water is actually going to percolate down into the soil. So most of it goes down. We look around us and we see these rivers and lakes, and we say, oh, wow, there's a lot of water there. But it turns out there's actually a lot more water inside the ground, and obviously in the ocean. And we'll talk about that in a little bit. And so you have all of this water that forms in these underground aquifers here, but some of it also ends up in these lakes, and these lakes are usually in a situation where the ground is either already saturated with water, or there's the right types of rocks, so it can contain the water up here. And similarly, rivers are formed by runoff. It's snow melt runoff can famously form rivers. And in general, if you see a creek or a river near your house, that especially when it rains, it fills up, that's a good indication that the groundwater is already saturated, and so things are running off into that river. And so that in general is the water cycle. You have evaporation, it condenses into clouds, it eventually precipitates, and it keeps going round and round and round. Now, of course, there's other actors at play. You have things like plants. Plants will take up water from the upper soil as far as the plant's roots go, and it will use that water to transport nutrients down from the soil up into the leaves. It also uses that water as part of the photosynthesis process that we've studied in many videos, and a lot of that water gets transpired out. So once again, this is transpiration, essentially evaporation out of the leaves of the water. Over here, you see this word sublimation. That's going straight from the solid form of water, ice, into the gas form of water, or water vapor. And this will happen in situations where it's cold and it's very, 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 very dry. And you have, in general, low pressure. And so instead of going into the liquid state, right then the water molecules just start leaving as water vapor. Now, and of course, I said we're part of it. Well, how are we part of it? Well, we will drink some of this fresh water. Our bodies are actually mostly water. The cells in our bodies are 70% water. Everything we study in biology, water is a key environment for all of these things to occur. And then we use that water, and then we will get that water out of our body, and then it continues on as part of this water cycle. Now, one thing that I find really interesting as an organism that is dependent on fresh water, when people say fresh water, we're talking about water without salt as opposed to salt water. So we really need this water that's in the fresh water in this lakes or in this river, or we might dig wells so that we can get the water out of these aquifers. It actually turns out that very little of the overall water in the world is fresh water. And so let me show you this chart over here. I always knew that, but I didn't fully appreciate how little was fresh water. So of all the water on our planet, 97.5% is salt water. For the most part in our oceans, only 2.5% is fresh water. And even of that 2.5% fresh water, very little of it is what we traditionally associate fresh water, the lakes and the rivers. When I think of fresh water, I immediately say, let me go to a lake or a river. That's stuff that we could potentially drink. But most of it is actually in glaciers and permanent snow cover. So it's ice, snow that is just not melting. And it makes you think about what would happen if this stuff were to melt. And then you also have groundwater, which we could have access to. That's why people dig wells. So we're talking about, groundwater includes soil moisture, swamp water, and permafrost. But very little of the water is actually in lakes and rivers, which I personally find fascinating. It wasn't obvious to me before I frankly saw this chart. Now, another really interesting thing is how long, on average, water molecules might stay in different parts of this water cycle. So, going back here, you can imagine that a water molecule could stay for a very long time in the ocean, especially, it's going to be moving around depending on ocean currents and temperature and all of that. But you can imagine it could stay in that liquid form in that ocean for a very long time. And maybe it spends a shorter amount of time in a cloud. And people have actually studied this, which I find fascinating. I'd be curious to figure out how they actually got this data. But this is the average residence time for water molecules. And you can see here that water can stay in glaciers and permafrost for a very long time. We're talking it could be up to 10,000 years, and these are all rough numbers. It could stay as groundwater anywhere from 2 weeks to 10,000 years, I guess, depending on how isolated that groundwater is. It could be in the oceans and seas as salt water for 4,000 years. And we can look at all of these all the way to within living organisms. It'll stay about, on average, a water molecule will last about a week in the atmosphere. So that's getting water vapor, turning into a cloud, precipitating down, on average 1.5 weeks. And once again, these are averages. It doesn't mean that every water molecule will stay exactly 1.5 weeks in the atmosphere, but it's a pretty interesting thing to think about it, and it gives you a little bit more sense of, where all the water is and how it all works together with the water cycle.